Before the first stars lit up the darkness, before galaxies began their slow cosmic dance, the universe was a quiet, glowing fog, a perfect, uniform sea of energy stretching out into the void. It was a place with no landmarks, no shapes, no structure at all. But hidden inside it, a silent force was waiting. A master architect, patient and unseen, ready to build everything you have ever known. This is the story of that architect. This is the story of gravity. For billions of years, this force has been the blueprint of the cosmos, the sculptor of reality itself. It's the reason stars ignite, the reason galaxies spin, and the reason you are here, on this planet, listening to this story. The universe we see today, this breathtaking design of glittering filaments and deep voids, of spinning worlds and blazing suns, was not an accident. It was built, piece by piece, by an invisible hand that has been at work since the very beginning. This is the story of how that silent architect took a blank, glowing canvas and turned it into a masterpiece. This is the story of how gravity built our world. To understand the architect's work, we have to go back to a time before it could even begin. Imagine the universe when it was just a baby, right after the Big Bang. It wasn't the dark, empty space we know today. It was incredibly hot and dense, a searing, bright fog of particles and light. In this early time, the universe was a chaotic soup where matter and energy were tangled together in a furious dance. For the first tens of thousands of years, gravity was there, but it wasn't in charge yet. The outward pressure from all that light and energy was just too strong. If any tiny clump of matter tried to form, it was instantly blasted apart. The universe was expanding and cooling, but it stayed almost perfectly smooth. It was a kingdom ruled by light, and in that kingdom, no structures could be built. Gravity, the force that pulls things together, was waiting patiently on the sidelines. But even in this perfect smoothness, the seeds of everything to come were already there, hidden in the fabric of reality itself. They were tiny, fleeting ripples called quantum fluctuations. In the very first moments of the universe, some microscopic patches of space were, for just a fraction of a second, a tiny bit denser than others. These weren't even seeds of matter. They were just whispers of a possibility. These almost invisible imperfections were what the architect would need to get to work. They were the subtle flaws in the perfect design that would one day become the foundation for every star and every galaxy we see. The universe kept expanding and cooling. For about 50,000 years, light remained king, but a turning point was coming. As space stretched, the energy of the light spread out and became weaker, while the pull of matter stayed just as persistent. For the first time, the quiet, steady pull of gravity began to be felt. The universe was changing from a kingdom of light to a kingdom of matter. The fog was starting to clear, and the architect, after 50,000 years of waiting, was about to wake up. As the universe cooled, something profound happened. For the first 380,000 years, the cosmos was a hot plasma where light was constantly being scattered, keeping everything in a fog. But as the temperature dropped, protons and electrons could finally join together to form the first stable atoms of hydrogen and helium. This moment is known as recombination. And when it happened, it was like a switch was flipped. The universe, once a glowing haze, suddenly became transparent. Light was now free to travel across space. This is the very same light we can still see today as the cosmic microwave background, the faint, gentle afterglow of the Big Bang. first detected by accident in 1965 as an unexpected faint hum from every direction in the sky. This moment also marked the true awakening of gravity. The intense pressure from light that had stopped matter from clumping together was now gone. All that was left was a vast, dark universe filled with a thin mist of hydrogen and helium, and something else, ... something invisible. The stage was set, but the main character in this next act wasn't the normal matter we know. It was something far more mysterious and much more common: dark matter. Dark matter makes up about 85% of all the matter in the universe. We can't see it or touch it. It doesn't interact with light at all. We only know it's there because we can see its gravity pulling on the things we can see. In the 1970s, astronomers like Vera Rubin noticed that galaxies were spinning so fast they should have flown apart. The stars and gas we could see didn't have nearly enough gravity to hold them together. There had to be a huge amount of invisible mass providing extra gravitational glue. That invisible glue is dark matter. This mysterious substance was the key to everything that came next. While the new hydrogen and helium atoms were still being pushed around by leftover energy, dark matter only felt one force: gravity. So it began to collapse immediately. Those tiny quantum ripples from the dawn of time were now the active blueprints. In the spots that were just a little bit denser, dark matter began to pull in more dark matter. It was a slow but relentless process. Over millions of years, these regions grew, forming vast, invisible structures called dark matter halos. Think of it like trying to build a sculpture out of a fine mist. The mist just spreads out. But if you first build an invisible, sticky frame, a scaffold, the mist will begin to cling to it and take shape. Dark matter was that invisible scaffold. These dark matter halos created gravitational wells foundations that normal matter could fall into. Without this scaffolding, the universe might have stayed a mostly featureless expanse for much, much longer. But thanks to dark matter, the architect had its tool. Gravity, working through these dark halos, began to gather the raw materials of the cosmos. The thin gas of hydrogen and helium began to flow from the emptier parts of space toward these growing halos, like rivers flowing into an unseen ocean. The silent architect was no longer just waiting. It was building. With the dark matter scaffolding in place, the universe began to change. It was no longer a uniform sea of gas. It was developing a texture, a geography. This process wasn't random. It was elegant and organized on a scale that's almost impossible to imagine. The architect was building a vast, interconnected network that we now call the cosmic web. The structure formed from the bottom up. The smallest dark matter halos formed first, pulling in gas. Then, these small halos began to attract each other, merging to form bigger and bigger ones. Over hundreds of millions of years, all the matter in the universe arranged itself into a spectacular pattern. Picture a spider's web stretching across billions of light years. This is the large-scale structure of our universe. The cosmic web has three main parts. The most obvious are the filaments. These are immense, thread-like structures made of dark matter and galaxies, stretching for hundreds of millions of light years. They are the great highways of the cosmos, channels where matter and galaxies flow toward each other. Where these filaments cross, we find the second part, galaxy clusters. These are the busy cities of the universe. Here, gravity is at its most powerful. Hundreds or even thousands of galaxies are packed together, all orbiting a common center. These clusters are the biggest gravitationally bound objects in the cosmos, giant monuments built by the silent architect. Our own Milky Way lives in a small group on the edge of the massive Virgo supercluster. The last part of the web is perhaps the most humbling, the voids. These are the vast, dark, and mostly empty spaces between the filaments. They are cosmic deserts. While the dense regions pulled in more and more matter, the voids gave their matter away, becoming emptier over time. A journey through a void would be one of profound loneliness, traveling for ages without seeing a single galaxy. Yet these empty spaces are just as important as the filaments and clusters. They provide the beautiful contrast that gives the cosmic web its shape. This entire grand design was sculpted by gravity alone. Those tiny quantum fluctuations from the very beginning decided where the filaments would form and where the voids would open up. Then, over billions of years, gravity made those small differences bigger and bigger. The architect had drawn its blueprint. Now, deep inside the densest parts of this web, it was time to turn on the lights. For hundreds of millions of years after the Big Bang, the universe was dark. This period is called the Cosmic Dark Ages. It was a time of silence and shadow, filled with the invisible architecture of the cosmic web, with no light to see it by. But deep inside the cores of the very first dark matter halos, the architect was getting ready for its next great act, creating light. Inside these early halos, the hydrogen and helium gas was becoming more and more compressed by gravity's gentle, inescapable squeeze. As the gas clouds contracted, they got hotter and hotter. At the very center of the densest clouds, a battle was raging, gravity pulling inward and the pressure of the hot gas pushing outward. In the biggest clouds, gravity was winning. Eventually, the core became so hot, reaching about 10 million degrees Celsius, that something new ignited. Hydrogen atoms were forced to slam together and fuse into helium. This is nuclear fusion. And in that moment, for the first time ever, a star was born. A point of light blazed in the darkness, and the cosmic dark ages came to an end. These first stars, known as population third stars, were different from any we see today. They formed from the pure hydrogen and helium of the early universe. Early theories suggested they were all monsters, hundreds of times more massive than our sun. More recent simulations show that the primordial gas clouds were probably more turbulent, breaking up into clumps that formed stars of various sizes. It's even possible some smaller ones were created that could have survived to this day, but the most massive of them lived incredibly fast and violent lives. The more massive a star, the more intense the gravity at its core, and the faster it burns through its fuel. While our sun will live for about 10 billion years, these giants died in just a few million. Their deaths, however, were even more important than their lives. When a massive star ran out of fuel, gravity delivered its final dramatic blow. The core collapsed, triggering a massive explosion called a supernova. In that fiery blast, new, heavier elements were created for the first time: carbon, oxygen, iron, all the elements needed for life. These elements, cooked in the hearts of stars, were thrown out into space. This was a turning point. The architect, gravity, had not only created light, but it had also started a cycle of cosmic recycling. The enriched gas from these explosions cooled and collapsed to form the next generation of stars. This process would repeat over and over, with each generation of stars adding more of the building blocks of planets, and eventually, life itself. Gravity built the stars, and the stars built the elements. The architect was now working with a much richer set of materials. With stars now lighting up the cosmos, the great structures began to look more familiar. The dark matter halos were no longer just invisible scaffolds. They were active construction sites, blazing with the light of millions of stars. They were becoming the first galaxies. But just as a sculptor can use the same clay to create different shapes, gravity sculpted these new galaxies into two main forms: elegant spirals and majestic ellipticals. Let's start with the spirals. Like our own Milky Way, the formation of a spiral disk is a beautiful example of gravity working with another law of physics, the conservation of angular momentum. Think of an ice skater spinning. When she pulls her arms in, she spins faster. The gas and dark matter that formed a galaxy had a slight, random spin to it. As gravity pulled all that material together, the cloud shrank, and just like the ice skater, it started to spin faster and faster. This rotation created an outward force that balanced gravity's inward pull, and the most stable shape for it to settle into was a flat, spinning disk. The beautiful spiral arms we see aren't solid. They are density waves areas of higher gravity that move slowly through the disk. As clouds of gas and dust orbit the galaxy, they run into these waves and get compressed, which triggers a burst of new star formation. The brilliant, young, blue stars that are born in these cosmic traffic jams are what make the arms so bright. The James Webb Space Telescope has shown that early galaxies first formed thick, messy disks, and only later did the calm, thin disks we see today develop. But what if the star formation happens all at once? That leads to the other main type of galaxy, the elliptical. Elliptical galaxies are huge, football-shaped swarms of older stars. They don't have the organized structure of spirals because their first burst of star formation was so intense that it used up almost all the gas very quickly. There was no gas left to settle into a spinning disk. Instead, the stars were left to orbit the center in all different directions, like a swarm of bees, creating a smooth, glowing ball of light. Many of these giant ellipticals are thought to be the result of another of gravity's designs, galactic mergers. When two galaxies get close, their mutual gravity pulls them together. A collision between two spiral galaxies is a chaotic event. The neat spinning disks are torn apart, and all the gas is squeezed together, triggering a massive burst of star formation that uses everything up. The result is often a single giant elliptical galaxy. Our own Milky Way is on a collision course with our neighbor, Andromeda. In about 4.5 billion years, the two spirals will likely merge into a new, giant elliptical galaxy nicknamed Milkomeda, a final testament to gravity's power to both build and rebuild. As the architect continued its work, it also created objects that are the ultimate expression of its power. These are places where gravity becomes so strong that it warps space and time to a point of no return. These are black holes. A black hole is what happens when a huge amount of mass is squeezed into an impossibly small space. The force of gravity becomes so intense that nothing, not even light, can escape. There are stellar mass black holes, which form from the death of a single massive star. When a star more than 20 times the mass of our Sun dies, its core collapses under its own weight, crushing itself down into a point of infinite density called a singularity. But there is another, much larger kind of black hole. At the center of almost every big galaxy, including our own Milky Way, there is a supermassive black hole. These are giants, with a mass of millions or even billions of suns. The one at the center of our galaxy, Sagittarius A*, has a mass of about 4 million suns. How these monsters formed is still a mystery, but we know they are a key part of how galaxies evolve. As gas and stars fall into them, they can launch huge jets of energy that can blow away gas clouds across the galaxy, regulating how many new stars can form. It seems the architect also knows when to pause construction. The most dramatic display of this power happens when these cosmic titans collide. When two galaxies merge, their central supermassive black holes slowly spiral toward each other. As they get closer, they begin to stir the fabric of reality itself. Einstein's theory of general relativity tells us that gravity is the curvature of spacetime. As these two black holes spiral together, they send out ripples in spacetime, like two bowling balls spiraling on a rubber sheet. These are gravitational waves. In the final moments before they merge, the black holes are moving at nearly the speed of light, and the waves they send out become a frantic chirp. Then, they combine into one, sending out a final burst of waves. For a century, this was just a prediction. But in 2015, the LIGO experiment detected these waves for the first time, allowing us to hear the universe's most violent events. Since then, observatories like LIGO, Virgo, and Kagra have detected hundreds of these mergers. The most recent observing run, 04, which ended in early 2025, has more than doubled the total number of known gravitational wave events, giving us an even clearer picture of these incredible cosmic collisions. The silent architect, it turns out, has a voice after all. A voice that speaks in the language of vibrating spacetime. For most of history, we thought of gravity as a simple force, an invisible rope pulling things together. But in the early 20th century, Albert Einstein gave us a completely new picture of gravity, one that changed our understanding of space and time itself. Einstein's incredible idea was that gravity isn't a force that travels through space, but a property of space itself. He realized that space and time are woven together into a single four-dimensional fabric, spacetime. And this fabric isn't flat, it's flexible. Massive objects like planets and stars actually bend or curve the spacetime around them. What we feel as gravity is just us moving along the straightest possible path through that curved space. The classic analogy is a bowling ball on a rubber sheet. The ball creates a dip. If you roll a marble nearby, it won't travel in a straight line. It will follow the curve made by the bowling ball. The Earth isn't pulling you down with a rope. It is warping the space-time around you, and you are simply following that curve. The Sun holds the Earth in orbit by creating a huge dent in space-time that our planet is constantly falling into. This idea leads to some strange and wonderful conclusions. One is that gravity actually affects time. It's called gravitational time dilation. The stronger the gravity, the slower time passes. This isn't a metaphor. Time literally flows at different rates in different places. For the GPS satellites that orbit our planet, their clocks run just a tiny bit faster than ours do on the ground, because they are in a weaker gravitational field. If their systems didn't account for Einstein's theory, GPS navigation would fail in minutes. The silent architect doesn't just build structures. It also sets the pace of time itself. Every new observation, from the way massive galaxies bend light like a cosmic magnifying glass to the precise signals from merging black holes, has confirmed Einstein's theory with stunning accuracy. Gravity isn't just the force that builds things. It is the shape of the universe, the dynamic, curving fabric on which everything happens. The architect isn't just building on a foundation. It is the foundation. The architect's work isn't finished. Gravity is still pulling galaxies and clusters together. But for the last few billion years, it's had a competitor, a mysterious force working against it. We call it dark energy. While gravity pulls things together, dark energy pushes everything apart. It's a property of space itself, and it's causing the expansion of the universe to speed up. This was a shocking discovery, and it revealed a cosmic tug-of-war that will decide the ultimate fate of everything. On smaller scales, like inside a galaxy or a cluster of galaxies, gravity is still winning. Its pull is strong enough to overcome the gentle push of dark energy. But on the very largest scales, dark energy is the clear winner. The vast, empty voids are getting bigger, pushing the great filaments and superclusters farther and farther apart. Any galaxy that isn't already gravitationally bound to us is moving away at an ever-increasing speed. How fast the universe is expanding is described by the Hubble constant, but there's a puzzle. Measurements of the expansion rate in the nearby universe don't seem to agree with predictions based on the early universe. This disagreement, called the Hubble tension, suggests there might be something missing from our understanding of this cosmic battle, a mystery scientists are still working hard to solve. What does this mean for the future? For billions of years, gravity will continue its local work. The Milky Way and Andromeda galaxies will merge in a spectacular display of gravity's power. But while that's happening, the rest of the universe will be slipping away from our view. The accelerating expansion will carry distant galaxies beyond a cosmic horizon, their light forever unable to reach us. In the unimaginably distant future, the universe will become a much colder, darker, and emptier place. Stars will burn out. Over trillions and trillions of years, even the black holes are expected to slowly evaporate. The magnificent structures that gravity built, the stars, the galaxies, the great cosmic web, will all be gone. The architect will have laid down its tools. Its masterpiece, a universe full of structure and light, will have had its time, and a final deep silence will fall. From the very first ripples in a perfect, glowing fog to the ignition of the first stars, the silent architect has been at work. It wove the invisible scaffolding of dark matter, spun the graceful arms of galaxies, and carved the deepest wells of spacetime. Gravity is more than a force. It's the organizing principle of the cosmos. It's the patient artist that took a universe of chaos and gave it form, structure, and beauty. And this story isn't just happening out there, in the distant cosmos. It's happening inside you. The calcium in your bones, the iron in your blood, every heavy element in your body was forged in the heart of a massive star that collapsed under its own gravity. That star exploded, scattering those elements across the galaxy, where they eventually came together to form our sun, our Earth, and you. You are, in the most literal sense, made of stardust. You are a living, thinking piece of the universe that gravity helped build. The silent architect built the stars built the elements, and the elements built you. You are a part of this grand cosmic story, a way for the universe to look back and wonder at itself. And that is a truly beautiful thing to think about.